Hello, everyone, and welcome to our first talk of the CIIR Talks series this spring semester. I'm Negin Rahimi, and it's my pleasure to introduce you to our today's speaker, Faegheh Hasibi. She is an assistant professor in the data science group at Radboud University. In the fields of information retrieval and natural language processing, she particularly focuses on conversational information seeking and knowledge-grounded search systems. She received her PhD from Norwegian University of Science and Technology. She has served as the chair of the CIIR Steering Committee, general chair of CIIR 21, and program co-chair of CIIR AP24. She received Best Paper Honorable Mention Awards from CIIR 16 and CIIR 17. Now, so for people joining us online, please feel free to put your questions in the chat, and at the right moment, you can also unmute yourself and ask your questions. Youngwoo here will manage in Q&A and pass the mic to people attending in person here. And please take it away, Faegheh.
Great. Thanks. Hi, everyone, and thanks for the introduction. It's a privilege to be here and to present this talk on conversation personalization. Before I start, let me thank my co-authors, my PhD students and colleagues who have contributed to the research that I present today. And with that, let me start. So we have seen great developments in conversational agents, and much of it is caused by the advancement of LLMs. What we perhaps miss right now is usage of long-term memory and personalization in LLM-based conversational agents. Let me explain it with some examples. Imagine that we have a conversational agent, a user, so like Alexa that is at home, a user comes in, have a dialogue with the agent, and then after a dialogue, he leaves, he gets a recommendation, an answer, a response, and then comes back again for in another session, ask another question. So ideally, when a session is ended, for instance, here where the user wants to have some recommendation for a recipe for dinner, we want to extract a user profile. It can be in simple key value store like a table, or in using the concept of personal knowledge graph that has been presented by Christian Bollock and Tom Kenter, or similar to just like presenting user preferences in sentences, in words, like what we have seen in Trick ICAD last year. The point here is that we want to extract user profile, store it somewhere, and then later, when the user comes in for the next session, we would like to be able to retrieve from that user profile and provide personalized recommendation without asking the same questions over and over in subsequent sessions. Another example is in industrial setup, where we have some proprietary data sources. It can be, again, documents, products, whatever, or even intra-company terminology. So user comes in, it has some requests. For instance, in this case, it's about insurance, car insurance. Ask a question, then the agent has to retrieve some information, some personal information from the user, and then also looks into some proprietary data, something that the LLM hasn't even perhaps seen, like the general LLMs hasn't seen, and then generate some responses and recommend some personalized responses. Okay, so with that motivation and that background, I will be talking about three processes and three steps in conversational personalization. The first one is the data. How can we build scalable personal conversations? And then the second and the third part is about user extraction, preference extraction, and personalized response generation. Okay, so we would like to, okay, we are living in the area of data-hungry models. We would like to have some scalable data for training purposes to be able to train personalized conversations. So this is one property of the ideal data set that we would like to have for personalized conversation. The second property is that we want these conversations to be human written. The reason is that we would like to have access to actual and real user preferences and interactions so that they can inform us about the future of conversation personalization. We want to surpass the existing LLM models, so we need something more than the data that is generated by current LLMs. The third property is that we would like to have the conversations over multiple sessions, similar to what we have in CIIR for session search. And ideally, we want to have the conversations to perform both preference elicitation and recommendation. So all of these properties in total means that this is a highly non-trivial task if we consider the task to be done by crowd workers. So if we give the task to crowd workers or even human experts, the good point is that we can obtain actual user preferences, but especially for crowd workers, the previous research has shown that there is a poor engagement of workers, which leads to very low quality data. So at the end, people switch to using to hiring expert, which means that the process is not scalable. On the other hand, we have LLMs. Currently, people use LLMs to generate lots of amount of synthetic data. Of course, it's scalable, but there are concerns about bias and diversity of these LLM-generated data. And the data that is generated is not credible for future of conversational personalization. So we proposed LLMs. It stands for LLM Augmented Personalized Self-Dialogue Conversation Creation. The basic idea here is that we have a human that switches between the role of user and system. It performs self-dialogue, and then when it wants to generate system utterances, it gets guidance from the LLM. So this is how the method works. It's like a high-level view. So we have a dialogue act classifier. It says the next action that should be taken in the conversation. The act could be preference extraction or recommendation or greeting whatsoever. Then this act is given to LLM, and the LLM generates some guidance. The guidance can be also based on the previously curated preferences of the user. And then once this guidance is generated, it is passed to the human. Human takes the guidance, write the utterance himself or herself, and then switches the role to user. Based on this user utterance, then we give it again to LLM, and then this process continues until a session is complete. And for this preference memory, you can think about it as a simple key value store, right? So once a session is completed, then we have a post-session part where we have the previous session, and then we give this session, basically the current session that has been created by the user. We give it to an LLM. The LLM extracted some preliminary preferences automatically. Then these preferences are shown to the user. Users verify them. And then once verified, they are passed to the preference memory. And then this process continues. Okay. So we wanted to evaluate this labs method with existing methods for dataset creation. So the methods are like, okay, what would happen if you have human-human interaction, self-dialogue, LLM-human, or LLM-LLM methods? With the criteria that I mentioned before. So for human-human, we failed due to the high dropout of workers when we wanted to pair them. And this was due to the complex nature of preference elicitation over multiple sessions. The same happened to self-dialogue setup. So we try to guide workers with some predefined responses and ask them to rewrite those responses, but they simply went for the default setup, and it resulted to homogeneous dialogues, which were not representative of a complex task that we had at mind. Then we had the LLM human method, where the LLM played as the role of an assistant. And then similar to the previous case, we again got homogeneous dialogues even after human rewriting and multiple temperatures. So here we are really looking for different scenarios, different trajectory of preference elicitation and recommendation. Then we had the LLM method, where LLM played both as the role of user and agent with some personas. And so we didn't, this was of course scalable, but it is not based on obviously real user profile and interaction. Even in that case, we tried to evaluate the diversity of the generated dialogues using distinct and entropy and self-loop. So these are all reference-free diversity metrics. And what we realized is that synthetic dialogues are obviously less diverse. This is also in line with the existing literature on diversity of LLM-generated data. And it also emphasized that when we want to collect this non-trivial task, it is important to carefully guide the users to generate responses instead of showing them what they have to do. And which in that case, we obviously received higher diversity, both in terms of lexical diversity and the overall trajectory of the dialogues. Okay, what about the scalability? So we just ran an instantiation of this model, this method, and then we were able to collect around 1,400 dialogues for multiple domains on movie and recipe. And the collected dialogues were up to 3 sessions. So this is what we asked the users for different scenarios for every session. And as you see, the number of dialogues that were collected were 3 times more than similar data sets for preference elicitation, which were done by human. So this CCPEM and MG-sharp dialogue. The numbers are even somewhat comparable to the persona chat gen, which is like a method that automatically generates chit-chat conversation based on personalities, which is fully synthetic. And the other data sets that are shown here are like for task-oriented dialogue, template-based models. So these are obviously less diverse, but of course have more number of dialogues. So in general, using this method, generation of scalable multi-session human-written personalized conversation is doable, and we could even couple this data set with around 11K preferences for recipe and movie domains. What about the diversity and quality? So we also evaluated the quality of the data set automatically using UniEval, which is again an LLM-based reference-free evaluation measure. And here you see how the labs dataset stand in comparison to the dataset that I mentioned before. Okay, let me pause a little bit, see if there are any questions, and then if not, then I'll go to the 2 other parts.
There are any questions?
Can I ask a question?
Sure.
I know I'm not there with you, Youngwoo. I'm just curious, and maybe this will come up later. Are these preferences considered fixed? I mean, you want the preferences to persist across time, but what if the preference is ephemeral? Like, it's cold outside today, so I want a warm meal. But then a little later, it's hot outside, so I want a cold meal or something like that. Does this accommodate that, or are they tend to be viewed as more fixed preferences?
Yes and no. So we had some fixed preferences, let's say like dietary requirements, like if you have some allergies or something like that. And then temporal preferences, like, okay, I want to cook something for dinner, I want to cook something for lunch, or I want to have a movie for this scenario where I'm with my friends, and then a horror movie for another scenario. So we try to collect all these even temporal preferences, but after every session, we don't necessarily delete or, let's say, edit or take into consideration the preferences that has to be edited, right? So it's the user that after every session defines whether these preferences are correct based on this last session or not.
Okay.
Later, if you want to use it for response generation or preference extraction, so that's the task that you want to deal with later on. So the data as it is considers those, but doesn't do any fixes or anything like that.
Cool, great, thank you.
Yeah. Okay, great. Let me go to the preference extraction part, which is like a natural step after this labs data set and method. So the goal here is to extract user preferences from a dialogue session, or in general a dialogue. And then the important point here is that we want to perform extraction once a session is complete, not during the conversation, because the user might change the preferences, or there might be misunderstanding between the human and agent. So the task is that we want to extract these preferences after a session. So here we use the LLM fine tuning. So we saw it as a sequence to sequence labeling task. We fine tuned an FLAN T5 model with some instruction prompts, which takes a preference category and a dialogue as an input and extract preferences. So here the preference category is fixed. We want to extract the values. So this is a very simple model. So we had two domains, recipe and movie. So for recipe, we have around 1,000 dialogues, and for movie, we have around 400 dialogues. What we did is that we trained the model or fine-tuned LLM for the recipe, and then we performed domain adaptation. So here, this line is without domain adaptation. This line is with domain adaptation on the movie domain. So what we want to show here is that when we have even larger dialogues for a certain domain, we can, using a domain with larger conversations here in this labs dataset, we can even adapt to the domains with less data, and the domain adaptation worked better. So that was a very simple addition to the labs dataset. But let me talk more about entities that appear in the conversation. So this is another work back in 2022 that we did with Hideaki Yoko. So in the focus here is that we have a user and system. So so of course the user might refer to some personal entities, and then later on refer to them like with pronouns like my cars, which reflect back to the live or pilot which were mentioned in the previous sessions. So if we are able to connect this personal pronoun like my car to the actual entities, we have enriched representation of users' personal entities and preferences and belongings, right? So so this part is obvious. So this is like doing entity linking for the conversation, but we want to also do this co-references. So what we do is that we first, so we propose a method to do that. So first we do the concept and named entity linking. So this, we did it by fine-tuning BERT and an entity linking method, REL. So this is the Radboud entity linking, which has been previously proposed for entity linking in documents and text. And so in this case, we particularly fine-tuned it and trained it for conversations using some conversational entity linking datasets. Then we have the personal entities. So we first do the mention detection of these personal entities, and then we link those personal entities to the corresponding concepts or entities that were mentioned in the previous dialogue terms. And for this, we use the co-reference resolution methods. So simply, let me just explain it with some examples. How we do it. So imagine that we have this utterance in some previous conversation, 2 cars, Honda Life. And this is a mention to an entity. So for every mention, we generate a representation of this mention. So this is like a trainable weight. This is a vector that is identified by a transformer. So here in this case, we use longformer. And then we get this mention representation. So what we do is that we try to, for any mention, entity mention and the personal mention, we try to obtain a score. So in this score, we have the mention that appeared previously. So we have the start of this mention. here we have some B, which is like some trainable weights. And then here we have dimension that appears after in a later utterance, the personal mention. And here we look at the start point, then we do the same for the end point. So we do keeping the start point of the previous mention and the end point of the next mention. So we do similarly for the end point of the entity mention, and then the start point of the mention, and then the other way around. So once we get these scores, we do it for all the mention pairs in the conversation dialogue, and then for every personal mention, we get the mention with the highest score according to this representation. So here is the conversational entity linking with REL together with this co-reference resolution method for extracting personal conversation, and obviously we get better results, but this is not just as results, so you can also use it as a package. You can go to this REL. It's also an extension of the REL entity linking method that is developed at Radboud. And the extension for conversational entity linking is also there. So using this conversational entity linking, we can further use these entities that are mentioned in the dialogue to build user profile in the form of, for instance, a personal knowledge graph, which can be later, every entity in this personal knowledge graph can be connected to an external knowledge graph like Wikipedia. All right. So I want to go to the last part, which is the personal response generation. Here the goal, by the way, before I start, is there any questions about also this part? Yes?
No,
Okay.
I think there's no questions in the room.
Okay. Okay, let me then go through the personalized response generation. So the goal here is that we want to generate personalized recommendation based on users' history and user profile. I said that it's good to have extracted user profile, but one might argue that, okay, given the LLM's ability in handling long sequences of text, do we really need to do this extraction? And if we use this extraction, okay, we want to further use it for in LLM prompt. So does it really worth the effort? So we wanted to look at this question, and then what we did is that we used a simple method to prompt an LLM to give us responses based on two scenarios. So one is like, okay, what do we do? What happens if we have a standard naive prompt where we give the LLM a previous conversation history and ask about it to provide personalized response or personalized recommendation. And in the second part, we wanted to have a memory-based prompt. So here we used the previously extracted preferences from the conversation. We give it to the conversation, to the LLM as an input to the LLM prompt. And then we matched it with the history of the current session, and we looked at the results. So, so for this, we evaluated the generated response, personalized responses using human on two aspects. One is rational and the other one is relevance. What we observed was that when we use the memory, it is very effective, especially for the rationale of recommendation. And this is a critical factor because if you want to have transparent and explainable recommendations, using memory, it already enables better reasoning of the LLM to generate responses. And for the relevance, we saw that for recipe we have better scores, but for movie we had almost a tie, and this was also due to the differences in the performance of preference extraction. So in the movie domain, the preference extraction was less effective than recipe. So that was also affected in response generation. So we wanted to do the automatic evaluation of this personalized response generation. What we noticed is that rouge and blue scores, these metrics that are used for translation, they assume significant overlap between ground truth and the valid responses, which are not necessarily the case in conversation personalization. So in personalized recommendation, we have highly diverse responses. And when we use rouge and blue, so the scores that they capture doesn't have any correlation with human evaluation. Because of the length of the conversation and also the complexity of the task. So a recommendation can be highly relevant and highly personalized, but it doesn't have any overlap with the ground truth response. Okay, so we tried to look at it at a different aspect. So we tried to see what is the utilization of the preference in the generated response. So we wanted to measure this factor. What we did is that we tried to compute precision and recall based on the overlap of the preferences terms that appeared in the ground truth and the generated response. And here we did mainly the exact match. So it tells us how these user preferences that appeared in the previous sessions help us to generate personalized responses. So this is a comparison of the two methods, standard and memory, evaluated based on the preference utilization. Sorry. So one thing that we observe is that we see a very similar trend to human evaluation. And then secondly, we also see that the prompt that is used for standard and memory methods is like threefold less than, so the prompt that is used for the memory is 3 times less than the prompt that is used for the standard method. So this is especially important for the industrial setup where we have a really huge number of sessions. So it is mainly impossible to have personalized recommendation without doing any enhancement of users' preferences. Okay. So let me do a recap of the what I mentioned in the beginning. So here, what I want to say is that we had a scenario where we had a user. In industrial setup, we have some proprietary data that a general LLM hasn't seen it. And we want to do some response generation and recommendation for this scenario. So what we observe here, what we want here is that we want to use LLMs, obviously. So we want to move from the pipeline approach that users, that in industrial cases use for evaluation, for recommendation in industrial setup. And we know that LLMs tend to hallucinate about less popular knowledge. So in order for conversational agent in industrial setup to provide response generation on their setup, we want to do some adaptation of the language model. Two methods that are used for the adaptation of language models are fine-tuning and retrieval augmented generation. When we are in less resource scenarios, fine-tuning means that we need to do an additional step of generating synthetic data, right? So we want to do, if we want to do fine-tuning for low resource data, we want to have, when we want to do fine-tuning for low resource data, we need an additional step of data augmentation. So let me look at the process that we designed to see how to adapt the LLMs for question answering on less resource domains. So the assumption here is that we have some documents. We assume that these documents are low resource. LLMs hasn't seen them at all, or in a very low frequent. So we generate. We have a retrieval model. So for the RAG-based approach, these retrieval models look at these documents and then generate some relevant passages. We take the first relevant passage and then we send it to a RAG model where we have all the weights are freezed. So this is like a model that just takes the top input and then provides a response. In the second setup, we have the Q&A that are generated synthetically by a model. So we take, for instance, a document, and then we break it into passages. And for every passage, we try to generate Q&A. Once we have this synthetic Q&A, we send them to an LLM, we fine-tune the model, all the model weights are changed, and then using that fine-tuning, we hope that the LLM has learned about this low resource setup, and then it can generate the answer. So the question here is that if you are in such scenario where we have, when we want to do response generation for on proprietary data, what is the best approach to take? Should we do the RAG-based or should we do the fine-tuning based? The RAG-based is obviously more demanding during the inference time, but the fine-tuning approach is less demanding during the inference because we don't need to do additional retrieval, but more demanding during the fine-tuning. Each of them has their own pros and cons. So what is the best setup to do? So in order to test this scenario, we experimented with the PopQA dataset. So PopQA is a dataset that is generated based on the factual knowledge in the knowledge graph. So every triplet, some triplets in knowledge graph, for instance, here in Wikipedia, are taken, they are converted to a question, and then for every triplet, which is a entity, relation, and entity, we ask a question, and the answer is another entity. So this dataset, in this dataset, we have the factual questions about entities of different popularity, and especially we have a large amount of data on long tail entities. In this setup, then we can see how performance on long tail entities is affected by these two approaches. So what we do here is that we take the Wikipedia article. So this is very important. So in order to simulate the industrial setup, we don't do the retrieval for the whole Wikipedia, but only for the documents that are in the PubQA dataset. So we limit ourselves to the documents that are in the PubQA dataset, only those Wikipedia articles, and then so we assume that this is a simulation of the industrial setup where we have only limited document that has been seen less frequently by the LLM. So for every, we take the Wikipedia article, we break it into passages, and then we assume that the summary paragraph of the Wikipedia article has the relevant answer to the questions that are in the PubQA, which is an educated assumption and guess. Okay, so now as a first part, we look at the performance of different retrieval models on this data set. Here again, these retrieval results are not on the whole Wikipedia, but on the data sets, only on the articles that we are asking questions about. So what we observe here is that if we take the summary of Wikipedia, the first paragraph of Wikipedia as a relevant passage, what we observe here is that we have higher recall for low popular entities. So we looked at the recall at 1. So we see that in general, both sparse and dense retrieval models have higher performance for less popular entities, and this is due to the possibly due to the limited occurrences of noisy passages for these low popular entities compared to high popular entities, right? And here by popularity, we look at the page views of Wikipedia articles over time, which by different resources, we know that it has correlation with the amount of time that LLM has seen information about entities during training, right? Okay, so keep that retrieval performance in mind. Now we want to look at the result of RAG versus fine-tuning on this data. So this is a plot where we compare different methods for this data set. So no fine-tuning, no RAG, and then other scenarios where we have no fine-tuning with RAG, different retrieval models, the DPR, and the ideal model here is the scenario where we use the summary of the Wikipedia article as an input to the RAG model. So we have the best retrieval model, or the best input for the RAG model. Okay, so looking at this plot, so this is a Flanty5 small. Looking at this plot, we see that these two lines, they show that we don't, so here we just do the fine-tuning without any RAG. So they show that fine-tuning, of course, enhances the performance, and this is especially true for the most and least popular entities, right? Okay, then we add RAG on top of the base model without doing any further fine-tuning. So this is the base model without fine-tuning, and then we see consistent improvements. Obviously, RAG helps more than fine-tuning. Then to the last part, here these lines, it's a combination of RAG plus fine-tuning. So we see that RAG plus fine-tuning outperforms the previous setups. Of course, here we have more cost for both fine-tuning during training and inference, but also what we see is that as the model size increases, so here we have T5 small and then base and large, we see that this benefit of fine-tuning plus RAG diminishes diminishes as the model size increases. So we almost see no differences in BERT large model or in T5 large model, right? We also did, so we also wanted to look at the effect that fine-tuning have, the effect of fine-tuning and RAG based on the retrieval models and the data augmentation model. So what we do here is that we have two methods for Q&A generation. So one is an end-to-end model based on this paper that has been published in ACL Finding 2023. And then we also do a prompt-based Q&A generation using CIIR. So the quality of the questions that are generated by the prompt-based model are higher than the end-to-end model. So what we observe, so here we have a more controlled scenario. We do more filtering and better generation of Q&A. So what we observe here is that when the Q&A quality, the synthetic data generation and data augmentation improves, we also see improvement in the fine-tuning model, in the RAG and fine-tuning models. And this is consistent across different models. The same goes for retrieval models. So we also saw it in the previous setup. As the performance of the retrieval model increases, we also see improvements in the RAG model. So whatever setup that we use, they are also affected by the retrieval or the data augmentation model in the previous setup. Okay, so I want to have a discussion here that, of course, we talked about conversation personalization. We know that we had a paper in 2020 that we discussed that conversation personalization is like a double-edged sword. So on the one hand, if we do high personalization, we have bias, but on the other hand, we want to have user satisfaction. We want to accommodate user preferences, but we don't want to create an echo chamber. So what is important in this setup is that we keep the users in the loop, and we allow them to understand what we collected from them, and allow them to create, modify, edit, delete whatever from these collected preferences. And in order to do that, we have to extract preferences in a way that is consumable for users. So we cannot present them large amount of textual data that is difficult to make sense of, or some embedding representation. Even if we do that, we should be allow users to do to be on top of what we have collected from them, so that at least the personalization is more controllable, and we also have a control over this echo chamber and bias effect that we might reinforce by doing personalization in conversations. So to wrap up, so I want to emphasize that user-centered dataset construction is important for conversational personalization and for the future development of conversational personalization, and it is doable by careful guidance of the users. When we extract user preferences in a semi-structured format, we enable and enhance rational and transparency of personalized conversation models. And when we are in the scenarios where we want to provide response generation on less resource data in conversational setup in Q&A, so it's best to use the RAG models, so they are more effective, perhaps less effective during the inference time, but in general, they are less prone to hallucination. So with that, I conclude this session or this talk, and looking forward to the questions.
Thanks for the speak. Let's give a claps the speaker. Any questions?
Hi, thanks for your talk. One question that came to my mind when you were explaining the data generation, one thing that happens a lot in conversations between an assistant and a user is the misunderstandings that the system might not know what exactly the intent of the user is. With the data generation in labs, that is kind of self-dialogue and the user switches their role between the assistant and user. They kind of know already what their intent was when they assume the role as a user. So when they switch their role to the system, they always know what the user wants. So maybe uh, those generated conversations would be less diverse in the sense that sometimes the system might misunderstand. Um, wouldn't that make a problem for the diversity of the data set?
Yes, that is indeed the case. When we have two users, there is so basically there's no assumption that that some contextual information is known by the assistant. But I also want to mention that even in the cases where the user and systems are two different people, two different agents, we also see that it is assumed that some background information is known to the assistant. So we have also seen it in other data sets. So I would say it is somewhat inevitable in collecting conversational data. So for instance, when the two people are having a conversation, for instance, in US, and there is a question about London or some ambiguous terminology, then the two people don't even ask about what is the background assumption. And we have seen it even in the dialogues that are created by two different humans. So the bottom line is that yes, that is the case, but that's also inevitable, and probably it is more in self-dialogue scenarios. Here we have preference elicitation, so we hope, or at least what we have seen is that these cases happen less often because the emphasis is to extract basic information from the users.
Thank you. And any other questions?
Hi, thanks for giving the talk. When you're introducing the equation for computing the name entities for reference, I noticed that you just use the first word and the end word. So I'm more curious about how did you get the equation? I mean, so for example, in some name entities like the location, so it may cover multiple words. So how would you equation fit this scenario?
Let me go to the slide and make sure that I understand the question correctly.
Yeah, this one.
Right. So here you are talking, you are saying that a mention can have multiple words, right?
Yeah.
And then we want to make sure that we consider all the words, right?
Yes, for example, the Honda here itself contains sufficient information, but in some other cases for Los Angeles, so the two words, the first word and the second word, they both they combine it and they refer to a location. And in your school, it may not reflect such. I mean, may discard the second word if something if the name entity is more complex.
Right. Yeah. So here, what we do is that, of course, when we do the mention detection, we know the boundary of the mention. So we have the start and the end, and we look at the embeddings that are obtained from a transformer model, a long former. And yes, for some cases, the embedding has less for this single term. Loss, for instance, versus Honda has less information or less meaningful. But when it's combined, or basically by training this model, when it's combined, then we get a ranking of all the possible mentions, previously mentioned mentions in the conversation, and then we are able to find the corresponding mention. So at the end, it boils down to a ranking problem, and yes, when there is a case that the first term or the last term doesn't have a full meaning, as we know, as we human can interpret, then still, since we combine them, it gives some information, right? So it all boils down to the embedding that is generated by the transformer model.
Yes, thanks. I'm just thinking that it would be good if you have some evaluation of the performance of this question. So for example, by comparing some similar equations and then compare the performance with some like other annotations. Thanks.
Right. So let's take it offline, and then we can discuss the evaluation results according to the paper. Yeah.
Yeah, and any last question, possibly? Also, I have one question about the user preference that incorporate the memory-based one and prompt-based one. I find that the prompt and the memory length is quite short. So I was wondering if there is some selection process, or do you assume that you just have some relevant information only? And would that be realistic in the practical scenario, or would there be any challenges in selecting this relevant memories or the prompt?
So you're talking about the length of this standard setup, right?
Actually,
That
both.
you assume that, so you consider that it is somewhat, the number of tokens is somewhat low, right?
Yes, it could
Yeah.
be larger in practice. So yeah.
Indeed, it could be larger. So here we only included at most 2 sessions. And and we didn't do any pre-selection here in the standard method. So it's really raw conversation history without any pre-selection. The actual selection is here in the memory step. So where we have the user preference memory, like the key values, and the conversation history up to that point.
Okay, so it's more like the previous context being summarized rather than very long, information summarized. Yeah. Okay, thank you.
So it is the information from the previous session that is summarized.
Yes, I see.
Yes.
Yeah, I think it's about the time, and we should wrap the question. And we'd like to thanks for your great talk and this attendance.
Great. Thanks for the Q&A.